our next speaker is actually doing קפיצת הדרך. Dr. Yonathan Cohen is fresh out of the oven of Weizmann Institute, and he's the co-founder, CTO of one of the most intriguing startups in Israel in the quantum field due to a disruptive approach. So the stage is yours.
All right. So if quantum mechanics hasn't profoundly shocked you, you haven't understood it yet. These are the words of Niels Bohr, one of the founding fathers of quantum mechanics, who we see here in this picture, together with Albert Einstein, of course. Actually, Einstein himself was so profoundly shocked by quantum mechanics that he really had a hard time accepting this theory. But shocking as it is, we now know that quantum mechanics is the most precise theory of nature ever invented. And so one of the more interesting questions which were asked in the last couple of decades was, can we use this? Can we take advantage of this strange quantum world? And can we make it work for us? And more specifically, can we build computers and other technologies that are based on quantum mechanics? And can these technologies perform any better than our regular technologies or classical technologies? And I will focus specifically on quantum computing, since this is what I'm working on, and this is what I was asked to do. And while the answer, the theoretical answer to all of these questions of whether we can build a computer, a quantum computer based on quantum mechanics, which can perform better than regular computers, while theoretically we know for a few decades that the answer is yes, it now seems that we're starting to get pretty close. So you probably heard about quantum computing. It's been in the news quite often recently, you know, with many of the tech giants of the world introducing their latest developments in the field. Their quantum cloud platforms, like Tal mentioned, by IBM. And you might have heard about the announcement by Google that it achieved quantum supremacy, again, just as Tal discussed just a few minutes ago. So quantum computing is generating a lot of buzz and a lot of news in the last few years. And the reason, of course, why these computers are so interesting to so many people and so many companies is this immense computational power that these computers are expected to bring with them. So this was the announcement by Google. So the most well-known example for the potential of the quantum computer is the RSA problem. So the RSA is the most commonly used encryption protocol on the internet. It's the encryption protocol that we all use to secure our money, our information. Basically, a lot of what we do online is secured by the RSA. And the RSA is based on a very hard mathematical problem. And in fact, a classical computer, a regular computer, can solve this problem, but it can do so in only billions of years, okay? So a classical computer can break the RSA, but it would take it billions of years. A quantum computer, a large-scale quantum computer, a very large-scale quantum computer can do it in about 1 hour, okay? So again, this is a large-scale quantum computer. We're not there yet. We're very far away. But it's something that it's quite imaginable given the great progress of the field in the last few decades, okay? So again, I was asked to give a sort of a more scientific talk, an introduction to quantum computing. This is what I'll try to do in this talk, and at the very end, I hope to talk a little bit about also what we do at Quantum Machines. All right. So you see from this basic example that quantum computers and classical computers are very, very different on a fundamental level, right? The difference between 1 billion years and 1 hour is something very fundamental. It's not about the size of the components of the computer or the architecture. It's really something in the very basic rules of nature on which these computers are based on. So I'll try to talk a little bit about that to sort of give you a little bit of background. And again, so how much time do I have, by the way?
25.
All right, so quantum computing in 20 minutes.
Yes.
Let's do it. So, okay, before we talk about quantum computers, we need to discuss briefly how classical computers work, okay? So classical computers, in every classical computer we have a memory, of course. This is how we store information in a computer, right? And each memory unit, each little memory cell, can either hold a 0 or 1. This is what we call the bit of information, the classical bit. And in fact, any system in nature, any physical system that has two different physical states can form a bit, okay? So for example, in your computer, we have many tiny electrical wires, okay? And each wire can be at 0 volts, this is an electric voltage, or at 5 volts, okay? This is some electrical voltage. And this is one way to form a bit. We say that if the wire is at 0 volts, it's in the 0 state. This is how physicists denote states, okay? And if the wire is at 5 volts, then this bit is in the 1 state, okay? But there are many other ways to form a bit. For example, in your CD-ROM drive, if you zoom in on the surface of the CD-ROM, you will see that there are, a little surface area, and each surface area can either be flat or it can have a little bump on it. So again, two physical states, 0 and 1, okay? And this is how we store information on the CD-ROM. And there are other ways to form bits, for example, in the flash memory drive, and so on. So there are many ways to form bits in the computer. And so again, a bit is a system that has two states, but we can now take more bits. For example, a system that has 2 bits will have 4 states, right? The 2 bits can be both in 0, 0, 1, 1, 0, 1, 1. And if I take more and more bits, I have more and more states. So 8 bits will have 256 states. And then I can take these bits and I can start making them go from one state to another and to another at every point in time, okay? This is called manipulating the bits or processing the information, okay? And this is, we do this in the computer using the second building block of a computer, which is called the gate. And so the gate is a little device that performs some function on the bits. It gives some input bits and it processes the bits somehow and it gives me some new bits. So this is how we can make bits go from one state to another and to another. And this is essentially a computer, okay? On a very sort of high level, abstract level, a computer is just a machine that has many states, okay? Many different states, all the combinations of zeros and ones that we can have with billions of bits today. And it just goes from one state to another and to another and to another according to some program, okay? According to how we wire all these gates, okay? And this is essentially an algorithm going from one state to another until we reach some final result, which is the result of the program or algorithm, okay? And computers in the last 50 years have become very good at performing these programs, at executing these programs, and this is due to Moore's law. Right? The fact that we are doubling our computing power every about 2 years, a little bit less. And we do that by doubling the number of transistors on a single computer chip, on a single piece of silicon for the same price. We're doubling the number of basically the gates, okay? These transistors that we form in silicon are the basic building blocks of the gates. And so we're doubling the number of gates that we can perform with a single computer chip. And this is really the fundamental reason for why technology has advanced so fast in the last 50 years, okay? It's not software, it's not even machine learning, it's really the fact that we're doubling the number of transistors in these tiny chips of our computer. But it's becoming very difficult. In fact, Moore's law is slowing down. And one of the main reasons that it's becoming difficult is quantum mechanics. So we already have quantum mechanics in these tiny transistors that disturbs the regular behavior of these classical computers. So perhaps we should start using these quantum effects instead of fighting them. But even if we do fight quantum effects and we continue to scale up classical computers with Moore's law for another 10 years or 20 years or 50 years, there are still problems that are too difficult for classical computers. This is a fundamental issue. There are certain problems that for classical computers, even if you double and double the computing power for another 100 years, you will still not be able to solve them in a reasonable time. For example, the RSA problem that I mentioned is such a problem. And this is why we base all our security on this problem, okay? And we think that, okay, we know that due to the rules of quantum mechanics, some of these problems are very easy to quantum computers, okay? So it's not just the fact that Moore's law is slowing down that we want to start using these quantum systems to do computation, but it's also the fact that the basic rules tell us that we can do something much better than in classical computers. So let me try to explain this now, okay? So we know now how classical computers work. Now how do quantum computers work? So I'll start with the basic concept that we have in quantum, the most famous concept that we have in quantum mechanics, and this is the concept of a superposition, okay? And this is the fact that while in the classical world we can have cats that can be either alive or dead, in the quantum world we can have a cat which is both dead and alive at the same time, okay? So you might have heard about the Schrödinger cat, right? It can be both dead and alive at the same time. We don't know how to do it with cats yet, but we do know how to do it, for example, with little particles called electrons or photons, as Tal showed before. Okay? So while in the classical world or in classical computers we have these bits that can be either 0 or 1 at every point in time, in the quantum world we can have things that can be in both 0 and 1 at the same time. Okay? In fact, it's not just that we call these systems qubits, okay? It's still a system that has two states, 0 and 1, but it's no longer restricted to be either 0 or 1, it can be in both, okay? And it's not just that it can be both, in fact, it can be in any combination of 0 and 1. So one way to think about it is in terms of a vector on a sphere, okay? So think about the regular bit, classical bit, being stuck to either the south pole, 0, or the north pole, 1. The qubit can be anywhere on the surface of the sphere, okay? So it can point anywhere, okay? It's kind of like walking on the surface of the Earth, right? Another way to visualize this is to think about, again, the classical bit is being in one of two states, so I can put the blue dot here, or I can put the blue dot here, but the quantum bit can have sort of different colors, okay? I can be a little bit sort of bluish in one state and a little bit more in the other state, okay? And now the even more interesting thing happens when we start to make a system with more and more bits, okay? So we said that the system of 2 bits has 4 states, right? 0, 0, 0, 1, 1, 0, and 1, 1. A system of 2 qubits can be in all of those 4 states at the same time, right? And so, again, if we think about this color scheme, then instead of being in either one of those 4 states, I can be in all of them with different colors in each one, okay? And the real crazy thing is that this scales up very, very quickly with the number of bits, okay? So just to give you a feeling, with a system of 4 bits, 4 quantum bits, or qubits in short, you can have 4 states at the same time, okay? If you had 30 qubits, the system can already be in 1 billion states at the same time, okay? And so we have 1 billion such dots, each one in different color, okay? And if we have a system of already only 270 qubits, the number of states that we can be in all at the same time is larger than the number of atoms in the universe. Okay, so this is a huge number, okay, a huge number. But why do we care about the fact that it's a huge number? Well, because it means that quantum computers can multitask, okay? While the classical computer is the system that just goes from one state to another and to another at every point in time, the quantum computer can sort of go in all of the different paths, we call them computational paths, or programs in parallel, okay? So while the classical computers goes in one program, just like from one state to another at every point in time, the quantum computer scans all of the different programs in parallel, okay? With a very small number of qubits. Now, there are certain issues with that. I won't talk about it too much, but as you can see from this picture, eventually we also end up with all of the results in parallel. We don't want to be in all of the results in parallel. So there's a subtlety here. I just don't like the fact that in popular talks, people stop with this nice picture of the quantum computer scanning all of the paths in parallel. It's true, but the problem is that at the end of the day, we also need to measure the computer, we need to look at this computer, and when we look at the result, we can only see a single answer. I mean, we are not quantum, we don't live in a parallel universe, we see single answers. There is a way to go around this, which I'm not going to talk about too much, but the key thing to understand is that it only works in some problems. In very important problems, just like the RSA problem and other problems, but it doesn't work in all problems. So it's not that quantum computers are going to replace classical computers for all problems. There are certain problems where we can take advantage of them in the following way. We can make parallel paths work together, sort of, to cancel out some of the answers to a problem, okay? And it's sort of like waves in the ocean. These quantum paths, they meet, right? When waves in the ocean meet, they can either cancel each other out, right? Make flat water, or they can make the water go larger. So this is called interference, and this allows quantum paths going in parallel to either cancel one another or add together to give us a higher probability to measure a certain result. And in some problems, we can use this interference effect in order to give speed up for the quantum computer, okay? So in these problems where we can design the quantum algorithm to use interference for our advantage, we can really beat classical computers. So again, it doesn't work in all problems, but we have a list of algorithms that we believe that quantum computers will solve much faster than classical computers, and these certain problems are relevant to many fields. Okay, so from computational chemistry, things like finding new drugs, designing new materials, or building more efficient solar cells. This is perhaps the first sort of applications for quantum computers through machine learning and optimization for many different industries, and all the way to cryptography, and as we discussed. So, okay, so how can we build these quantum computers? So, again, Tal talked about this a little bit, so I won't talk about it too much. I listed two examples of qubits that we actually use, physical qubits that people use to build quantum computers, trapped ions and superconducting qubits. There are many others, but these are sort of the leading ones today. So trapped ions are, you know, an ion is just like an atom, and so we can trap these atoms inside a vacuum chamber, inside what's called an ion trap, and we do that with lasers. And so think about it, each ion is trapped with laser beams, and here is a picture of such 3 atoms that were trapped, and then each one of these atoms serves as a qubit. The different orbitals inside the atom serve as the different states, and we can shoot laser beams at these atoms in order to perform the quantum gates, in order to make these qubits move from one state to another, right? Go through this parallel quantum paths. Okay, and so this is how a trapped ion labs looks like. And the other platform that I wanted to talk about is superconducting qubits. So this is the platform that is used today by most of the leading players like Google and IBM. Again, it's not the only one, but it's pretty much the leading one. And here we're making small circuits from aluminum. Aluminum, when it's cooled down to very low temperature, it becomes superconducting, which means it has no resistance to electricity. It basically conducts electricity perfectly. And so we can make qubits on a chip. And this is what you see here. You see a chip with 4 qubits. We have 1 qubit here, 1 qubit here, 1 qubit here. These are essentially, they behave as artificial atoms, again, as Tal mentioned. And we control them, instead of with laser beams, with microwave signals. So we can shoot microwave signals through these control lines here that you can see, these thick white lines. We basically shoot pulses that are similar to the pulses that your cell phone sends to the cell tower to communicate with it. This is how we communicate with these qubits. We send these microwave pulses to these qubits through these wires, and they also come back and we measure them. Okay, so we kind of speak with these qubits sort of, we build sort of a modem for these qubits. And again, we need to cool these chips down to very low temperature. This is the refrigerator used at IBM. You see this whole thing is a refrigerator. The chip sits down here at the bottom of this thing, and this thing is cooled to 10 millikelvins. This is 100 of a degree above absolute zero. And this thing gets sealed down. Oh, you see all these lines here. You see this is the lines that are used to carry these microwave signals to the qubits back and forth. And then this thing is sealed down. This is the white thing that you see there. And you see all the wires coming out of the fridge going to this equipment that produces the microwave signals. Okay, so this is how a modern quantum computer looks like, okay? The state-of-the-art quantum computer. What do we do at QM? Well, it's related to what I just talked about, because as you now know, a quantum computer has the quantum processor, which is where the magic happens, where we have the qubits. And we always like the analogy of a very strong muscle, because it can do this heavy lifting, right? This computational power that we talked about. But every strong muscle, even the strongest muscle on earth, needs another system that controls it and operates it, and this is the brain. And this is what we do at quantum machines. We make what's called a quantum controller, which is the machine that produces all these microwave pulses, or pulses that go to these qubits to operate them, to perform the gate operations on the qubits. Okay? Today, we are 20 people at the company. We have software engineers, hardware engineers, quantum physicists, of course. We already are selling our products. We sell to anyone who's making quantum processors, in fact working with many different kind of qubits. We already have substantial revenue. We have customers including multinational companies, startup companies, research labs, and academic institutes, of course. And we have more than 13 patents, forming the biggest portfolio actually in the field of quantum control. We have the most advanced system worldwide, of course, for controlling and operating quantum systems. Just one second. And we have people from Harvard University and Texas University helping us on the advisory board, and we're backed by Battery Ventures and TLV partners. So this is the system we're developing. We have a new programming language for quantum computers that is called QA. You program the quantum algorithm in our programming language, then it goes to our control hardware, which receives this code and translates it to all of these pulses that go to the qubit and operate it in real time. Okay? Yes, I think there was a question. That was the question, okay. Exactly. So we see ourselves as I mean, one of our goals is to standardize QA as the standard low-level language for quantum computers, on which you can then build higher-level languages in the stack. Okay. Yes, you can do that. Up to about, okay, with your laptop you would be able to do that up to about 30 qubits. With if you want to simulate 50 qubits, you would need the strongest computer on Earth. And if you go to about 54, 55 qubits, maybe 56 qubits, you will no longer be able to simulate this. This is the whole point, right? The point is that we cannot. Well, Richard Feynman, who actually was one of the first people who thought about this idea of a quantum computer, that's how he arrived to this conclusion that we might want to build a quantum computer because he realized that we will never be able to simulate quantum mechanical systems efficiently with classical computers. So you see, I have to keep track of all of like this exponential number of numbers, right? We saw that we have all these states, and each state has a different color, right? If I want to say what's the state of my quantum computer, I need to say this state has very strong blue. This is a little blue. This is no blue at all. This is very, very blue, right? And I need to tell you all of these numbers, which is an exponentially large number, and this is what I would have to keep track on with my classical computer. So at about 50 qubits, this becomes impossible for even huge supercomputers. But we can do that for small computers in order to simulate small quantum computers and see that our small actual quantum computers behave properly, and this is also related to how you would verify quantum computers. These are very interesting issues. Okay, so to maybe wrap it up, where are we with quantum computers? We as a community now, not quantum machines. So we are right in the middle of a quantum jump, okay? We're really right in the middle because up until a few years ago, we had quantum computers, very small quantum computers with 1, 2, 3, 4 qubits, okay? These were the first prototypes that showed that this could be done. We are now at about tens of qubits. And it's really right in the middle of the jump because this is where quantum supremacy is, well, not expected to happen, actually happens, right? So Google showed quantum supremacy with 54 qubits. And again, it's not exactly already, in the sort of big water of the industry, from the research world, because this is still not a useful algorithm. What Google showed is that they can perform something much faster than a classical computer, but what they can perform is something which is not yet very useful, okay? And at about hundreds of qubits, we hope to see the first real useful applications. So first useful applications of quantum computers, and this is where quantum computers would actually start to use, and we hope that this will happen in the next few years. The quality of qubits also has to grow together with the number of qubits. It's not enough that we just put more and more qubits on a single chip. We can actually put hundreds of qubits today on a single chip, but what really is blocking us from doing that is the quality of the qubits. The more qubits you put on your chip, the more noise you're generating on your chip, and it actually interferes with this quantum behavior. We're very fortunate in the last maybe 10 or 15 years that the lifetimes of qubits, especially superconducting qubits, have grown exponentially, and we hope that this trend will continue by very, very difficult engineering. So we sort of have now a sort of small Moore's law for qubits, and we hope that this trend will continue because this is the essential thing for scaling up. So I'll wrap it up with saying that this is really an exciting field, and it really is one of these disciplines that combines many expertise from many fields. So, okay, quantum physics, of course, but also computer science, defining algorithms and languages, and the software stack of the computer. Electrical engineering, of course, as you saw, we need to build very complicated systems to control these qubits. And all of this combined for quantum computing. So I think in Israel we really have the talent and the right people to push this field forward. So with that, let me thank you.
Thanks, Yonathan. There is already one VC in the back that asked for your name and maybe.